So my focus on my research is on nanoparticles. So I work with particles that are a billionth of a meter. And when you get to that size scale, some quite interesting physical properties change. So you get a difference in properties from that you would get in the bulk. And in particular, I'm interested in semiconductor nanoparticles. So those are particles have unique electronic properties. For example, they become fluorescent, and their fluorescence is entirely dependent on their size. So these fluorescent nanoparticles are called quantum dots, and the reason why they're called quantum dots is because they are quantum confined. The electrons within the particle are quantum confined. And this is a fantastic example of a particle in a box, something that you'll study in first year physics. So it's a real life example. And these particles are very strongly fluorescent. And what we can do is we can target them to actually attach to cancerous cells. And if we can target cancerous cells, we're able to image cancerous cells using fluorescence. And that will enable the early detection of cancer. These quantum dots are formed from semiconductor materials. And semiconductors have revolutionized our lives over the last 100 years. And quantum dots are just an extension to the semiconductor industry, really. So a semiconductor has a valence band and it has a conduction band. And in order to get these particles to fluoresce, you have to promote an electron from the valence band into a conduction band. And after some period of time, that electron will drop back down into the valence band and it will emit a photon of light. Now, the interesting thing is when the particles are shrunk down smaller, that band gap gets larger. So that photon energy will be greater. So that's the principle behind them.